Good afternoon, everyone, and welcome to today's Safer Sim webinar. Today, we will be listening to researchers from the University of Massachusetts-Amherst. They will be discussing a research project that they performed in Massachusetts. So I will let Dr. Mike Knodler, he will take over from here. And if you do have any questions, you can please use the chat box to the right, and we will address them whenever we have a chance.
Thanks, Jacob. Good afternoon, everybody. As Jacob mentioned, my name is Mike Knodler. I'm here along with Eleni, Christofa, and Sibi Samuel. And I also wanted to acknowledge a fourth of our investigators, Bhavana Gangala. She was a graduate student here at the University of Massachusetts and is now working for Green International as a traffic engineering consultant here in the greater Boston area. Today we're going to be talking about evaluating the effect of cross-sectional roadway design elements and its impact on driver behavior. And as many of the Safer Sim projects are, it involved simulation in some way, shape, or form. As Jacob had mentioned, encourage you to ask questions along the way. We'll answer some in real time and then save others for the Q&A at the end. The plan here today is to take 20-25 minutes or so, talk about the research that we carried out and some of the more interesting findings and what we did. As I jump in, just a little bit of background on Safer Sim, the University Transportation Center consortium that we have here at Safety Research Using Simulation. This was as a consortium led by the University of Iowa, but also includes the University of Wisconsin, the University of Central Florida, the University of Puerto Rico at Mayagüez, as well as UMass-Amherst. I know there's a handful of new participants. I would encourage you to go online to our YouTube channel and check out all of the great webinars that are posted there that are free, that are there for your download and utilization. A little bit of a geography lesson as well, just to get us rolling, so you have a sense of who we are and where we are. So usually when most folks think of Massachusetts, the first thing they think of is Boston. You see Boston out there in the eastern part of the state in on Boston Harbor. We're actually located about an hour and a half to 2 hours west of Boston, a rural area in Amherst, Massachusetts. We like to think we have a pretty campus, but I highlight these pictures just to say it's an open invite. So if at any point any of you would like to come, take a tour of the facilities, meet with us, talk about some of the exciting activities and research that's underway here at campus, by all means consider yourself invited. So today, a little bit more about us at UMass. Here's the four investigators that I mentioned. So Bhavana on the left, Eleni, who's here with me, myself, as well as Sibi. When we think about Safer Sim at UMass, there's really a couple different threads to the work that we primarily do. We have 4 different driving simulators here on campus with varying levels of fidelity. We weave them into many aspects of our research. We also employ a fair amount of virtual reality technology. But another resource that we make use of quite a bit in a lot of our safety-related research is our crash data warehouse. And it includes not only crash data, but citation data, commercial motor vehicle data, some levels of hospital data, as well as the typical normalizing data. So oftentimes we like to think that we slice and dice and analyze some of the data that we have. Once we complete the analysis, then we ultimately try to develop countermeasures, something that we might test in the driving simulator or one of our laboratory facilities, before we bring it out into the field or the naturalistic roadway environment. So today, like I said, what we're going to do, a brief little introduction. We'll outline some of our research methodology, talk a bit about our results as well, and then, more importantly, some of the conclusions as well as some of the ongoing and future research that we're currently in the process of completing. And, I know that the highlight talks about cross-sectional design, and we'll talk a little bit about why that's important. First, when we think about it, by way of a bit of background here, there's several different factors that influence the manner in which people drive, and we could probably spend an entire day just talking about those different factors. It includes the significant amount of visual information that drivers are being required to take in while they're operating a vehicle, the impact of other vehicles and the influence that it has on driving, as well as our own vehicle performance, and certainly the weather and other elements such as that. And when we put this together, we think about, well, what is the cause of crashes? And so, we relatively famous graphics and some numbers that I'm sure most of the folks on the webinar are familiar with. But the roadway environment is a contributing factor in 34% of crashes. Human factors are a contributing factor in 93% of the crashes, and the vehicle is a factor in 12% of crashes. And when we think about those, there's elements of failure in roadway geometric design as it relates to the roadway environment, speeding and aspects related to speed under the human elements, and certainly vehicle performance under the vehicle characteristics that come along with that. And when we put that together, we end up with a graphic, again, a relatively famous graphic, where we look at the contributing crashes and the overlap between each of those elements within the system, the vehicle, the roadway, and the driver, and certainly the area where they entirely intersect. And we think about numbers. It's why what we do, right? So on average, the 37,000 fatalities, from 2006 to 2010, or more recently the decrease, but now the fact that we're going back up again with respect to recent trends. And one of the bullet points that we hear about on a regular basis, and our own data proves that, is the impact of speeding related crashes. And so, one of the things that we have the opportunity to do as transportation engineers is to identify ways that we can mitigate the effects of speeding related crashes, and so that we can create an environment that makes it conducive to drivers traveling at the speeds that we ultimately want them traveling at. And so the front lines of speed management in many people's eyes is speed limits. And again, you could take an entire course on this. If you've participated in FHW or NHTSA speed management course, a big part of the course is all about setting appropriate speed limits. I know we have some folks participating from New York. We've got folks in Boston. You're starting to see more and more municipalities lower overall speed limits to 20 or 25 miles per hour in downtown areas. And one of the things that we know is, without a system-wide change, which is significant, if it's simply a roadway environment where it's not a total change within the town, but a roadway environment where all we do is change the speed limit, whether it's changing it up or changing it down, we know that the change in speed limit signage alone doesn't result in a drastic change in the speeds that we see on the roadway at all. And that's, again, whether we adjust the speed limit upwards or downwards, and by as much as 0 to 5 miles per hour up to 15 to 20 miles per hour, the average speed tends to remain constant, which talks about the need that the roadway environment has a significant effect on the speeds that people are traveling. And so when, again, you participate in different courses, there's a litany of different things that we can talk about with respect to roadway design. Context sensitivity, traffic calming, I'll talk a little bit more in a minute, but more commonly roundabouts or perceptual measures like some of the ones that you see here on the right, as well as vehicle activated speed displays, the notion of variable speed limits, which are popular in different parts of the country, and then the various roadway design elements themselves that we might think about. So from a context sensitivity standpoint, right, altering the roadway environment to create an environment that's suggestive of a different speed or a more appropriate speed, or certainly at the very least the changing context in which the roadway environment is changing. And then we think about traffic calming, and whether it's neck downs or speed humps or speed bumps or many of the different traffic control devices that are intended to reduce speeds as a result of their performance. But one of the things that we wanted to do in this particular study is, apart from traffic calming and other devices, is think about the left to right, the cross-sectional design elements on a roadway. And we were primarily focused upon two different variables, including speed and lateral positioning. And I'll talk about why those are significant. But if you think about the roadway cross-section, as we think from left to right, we've got elements that include the side slope, the cross slope. Do we have a curb, yes or no? Do we have a shoulder, yes or no? Do we have a bike lane, yes or no? Do we have multiple travel lanes? If we have travel lanes, how wide are the travel lanes? Do we have medians? And all of these different elements we know influence the speed at which drivers travel. And isolatedly, we can identify what some of those specific elements have on travel. And there's been no shortage of field studies over the years that have identified what the impact of changing a roadway from this to that would have on speed, or changing a roadway from that to that might have on speed. But we felt that that was somewhat limited, and here's why. There's so many other factors when you do a naturalistic study that would influence what behavior that you're seeing, and that there really hadn't been a true laboratory setting in which each of the variables was controlled. The drivers remained constant and studied their specific driving performance to make sure that what they were doing was consistent with what you'd expect. So what we'd done in this particular study is that we took the existing cross-section and we manipulated it across a number of different scenarios and had the same drivers drive each of these cross-section and observe several attributes related to their driving performance. So again, a really laboratory-based setting that allowed us to hone in on some of these specific roadway design elements and their influence on speed and behavior in general. So this slide is really what we know, right? And so we could go through again each of those cross-sectional design elements, but we broke it down into some of the more common ones that we think about, including the idea of narrowing the lane widths, or introducing bicycle lanes, or introducing raised medians. And with respect to speed and lateral positioning, we might hypothesize, what the influence of each of those roadway design attributes may be. So, for example, a narrower lane, we would expect to reduce the speed of at which the drivers travel. We would also expect in a narrower lane that participants might move towards the center of the travel lane, or certainly to the center of the right-of-way. We anticipate perhaps that a bicycle lane would introduce, not necessarily change the driver's speed, or if you could actually probably make a case of why it might go up or down, but wanted to know exactly what that particular influence. And then what would the presence of a bicycle lane have with respect to lateral positioning, or what would the presence of a bicyclist within a bicycle lane have with respect to lateral positioning? And similarly, when we look at raised medians and other roadway design elements, what is the influence on speed and lateral positioning? And our motivation for this study is really, we think we know these things, right? So we know bits and pieces of it, but what is it that we really want to know about these different roadway design elements? So I'll talk a little bit about our methodology and what we've done in this particular study. And it really starts here. So our case study was really born out of a stretch of roadway known as Burnett Road, and you can look it up on Google Earth if you'd like. It's a roadway not far from our campus in Chicopee, Massachusetts. This is about 1.5 mile long stretch of roadway, roughly 14-foot lanes, 8-foot shoulder. There's no median, and the speed limit on this particular roadway is posted at 30 miles per hour. And there's a bit of frustration on the part of the residents, on the part of the city itself, as to why nobody on that particular roadway travels 30 miles an hour. And again, we as traffic safety professionals could probably speculate pretty regularly or widely about why that might be. But we said, well, here's an opportunity, right? A blank slate, if you will. And so here's just a cross-sectional shot of Burnett Road and what it looks like. And we said, okay, so if this roadway environment right here is our blank slate or our base condition, what happens if we were to manipulate that? And if we were working with the city or town on this particular project, what might we expect as we started to introduce different roadway elements here? And so rather than just saying, well, if you narrow the lanes and then studying it before and after, well, what would be the combined effects of looking at different aspects in different combinations? And so the idea here was that this served as our base case, and then within this existing right-of-way, we continued to manipulate the cross-section to see what the impacts on driver performance were. And so what we done was we replicated this study, or replicated this stretch of roadway to scale in our driving simulator. And I'll talk a little bit about some of the attributes of the driving simulator in just a minute. So our base case was replicating what we'd seen in the field with respect to this stretch of Burnett roadway. And the idea here was that we manipulated the various pieces, various roadway cross sections in different scenarios. And so the 4 experimental scenarios, or the 5 total scenarios that we considered, was the base case. But then we also narrowed the lane, so we actually tightened the entire roadway section, so the roadway pavement, but again within the existing right of way. So we narrowed the lanes and shrunk the shoulder. In scenario 3, we introduced a bicycle lane, so we kept the travel lane as is. We introduced a 1-foot buffer, and then introduced a bicycle lane as we modified scenario 2 to become scenario 3. We also explored the impact of introducing a median, so keeping a travel lane the same, keeping a right foot shoulder, but then adding a center median between the 2 travel lanes. And then in the 5th scenario, we introduced a curvilinear profile. So we took the existing alignment, which was relatively tangent sections, and we introduced sweeping or gentle curves throughout the roadway environment so that we could study the effect there. And again, it was building off scenario 4, so it again still had a median, but was presented in a curvilinear fashion. And just a little bit more background with respect to curvilinear environments, right? So one of the things that we know from a network design or a neighborhood design impact, and is probably highlighted really well here in just these couple of graphics. So if you look at the 2 graphics on the left, if you start on the bottom image, you see that it's a straight stretch of roadway, and the top cross-sectional view shows that it's a relatively straight section of roadway, and the speeds are what we might expect. And the images on the right are that of a curvilinear roadway, where we've introduced more general curves, and we expect that the speeds in that particular roadway section are going to be slower as a result of that. And so wanting to understand what the impact of the roadway design would be. And more recently, in fact, some of our own work is actually starting to look at the impact of curvilinear roadway environments in other sections. So in particular, the entrance to a roundabout. So as you're approaching a roundabout, if you introduce curvature, what does it do to the approach speeds and ultimately the operation of the roundabout? And so one of the projects that we currently have ongoing that we'll talk a little bit more about later introduces varying degrees of curvature on the approach to a roundabout. And I'll just hint at this and say that some of our preliminary work is really quite positive in that we see that the approach speeds are significantly reduced as we modify the curvilinear approach as drivers are entering the roundabout environment. And so we can talk about this a little bit more. So getting into the apparatus, so our driving simulator is a fixed-base 1995 Saturn sedan, 3 screens, 150 degrees of horizontal view, and a resolution of 1400 by 1050. In fact, that number is probably a little bit off. And I'm happy to report that after almost 2 decades of spouting off those various statistics, we're actually about to upgrade our simulator next week, 2 weeks. We're going to upgrade our simulator, and so it will no longer be a 1995 Saturn sedan, but more likely a 2015 Ford Fusion, which is a big leap forward. But not only that, we'll also introduce the presence of 2 additional horizontal screens, so jump to 5 screens, as well as a 6th channel, which will be rear projection and simulator rear mirror. And then the other big part of our work is the mobile eye tracker. Our particular eye tracker that we used on this experiment was the ASL head-mounted, visual angle 50-degree horizontal and 40 degrees vertical direction. And then you see a picture of it there, where it's really not intrusive to the driver in any way, shape, or form. We put what amounts to the glasses or the goggles on the driver. It's got a scene camera so that we see exactly what the driver is, and then it overlays a set of crosshairs on the driver so that we know where exactly within the environment the driver is looking. So it provides not only the scene camera, but within the scene we are able to know where it is that the driver is looking. Now, some of you might at this point say, well, wait a minute, there's no way to replicate speeds in a simulator environment. You can't simulate many of the different applications that or different design features that we have in the roadway environment. And the reality is that's not entirely true. And in fact, one of our studies going back over a decade was just that. It was a validation of the use of simulators for speed-related research. And one of the things that we done was we replicated a stretch of roadway where in the simulator and in the field, and there were really 4 different layers to the previous work. The idea was to not only get a sense of what drivers were traveling at with respect to speeds, but also what drivers thought that they were traveling at. So for a sample of drivers, they drove both the simulator course, they drove both the field course, and at different points, their speed was occluded from their vision, and they were asked how fast they thought they were traveling, and then we also recorded the speed at which they were traveling. And so we matched up those values from both the field study with the exact same checkpoints from the simulator study, and identified how well we were able to do in terms of matching speeds. Now, the speeds in the simulator were a little bit faster overall, but the discrepancy between perceived and actual was identical, and so with a slight little calibration, we were able to know that the magnitudes and the changes of speeds were appropriate, even if the overall speeds were a little bit higher in the simulator environment. So just a little bit of background. So because we were taking an existing roadway and we were manipulating it, what we had to do was we couldn't just take the simulator files directly and use them. It involved a couple of different steps here. So for those of you that are more from the simulator community, this would be a similar methodology that's been used at a lot of different University of Wisconsin studies, as well as a number of different studies here at UMass. So we first start by creating the roadway environment in Civil and 3D, and then we export the 3D surfaces to another program, and in particular we import it into Blender, where we create the textures and we convert it into a virtual reality modeling language, or a VRML model, after which time we bring it into the simulator environment using their proprietary software associated with our RTI driving simulator. So going through these steps, did a couple of things. One, it allows us to take any geometry that we want and import it into the driving simulator in a relatively quick time frame. So if we want to take an existing roadway for which we have a civil 3D drawing, the idea of bringing it into a simulator roadway or simulator environment and driving it before you open it up in the roadway or start the actual field design process is relatively straightforward. But more importantly, for our particular study, what it allowed us to do is it allowed us to manipulate the roadway cross sections in the way that we wanted while holding all else constant. And so again, we were manipulating the 5 different roadway cross sections within the study here. So just a quick talk about our design variables. Our independent variables included things such as the lane width, the bicycle facility, the curb median, the clear zone, the shoulder, etc. Basically the 5 different scenarios, so the base case plus the 4 different experimental ones. And then our dependent variables were speed and lateral position. And we were really looking at how fast the drivers were traveling in miles per hour, as well as where they positioned or aligned themselves on the roadway with respect to the center line of the roadway. And we measured their lateral deviation in terms of feet as they departed from the center line of the roadway. And so here's just a graphic that kind of highlights how exactly we did some of this in this particular study. And so in terms of our experimental design, each of the 5 virtual worlds took on average 2 minutes. Our goal or our target was to keep the overall amount of time in the driving simulator under 15 minutes. This was to cut down on incidents of simulator sickness. For those of you that have participated in the simulator study before or have run them, certainly know that it is a possibility. We tend to see older drivers, we tend to see drivers with glasses, etc., other attributes associated with simulator sickness. We wanted to minimize simulator sickness, and one of the ways to do that is to minimize the overall amount of driving time, in addition to turns and several other things that we can do. So with that, we tried to keep the drives relatively short. Each driver that came in drove each of the 5 scenarios. So each of the drivers that came in drove each of the scenarios. Because we were working in multiples of 5 here, we ended up with 20 total subjects. I'll talk about that in a minute. We had no other traffic in the participants' direction of travel, but there was ambient traffic in the oncoming direction. So there was ambient traffic in the oncoming direction. And again, throughout the drive, we measured their speed and lateral positioning, and what we did was we opened this up at 5 different checkpoints so that we weren't running with 5 total roadway environments. We segmented each roadway into 5 different check stations or checkpoints, and within those checkpoints we measured vehicle speeds and lateral position for each driver within those lanes. And here's just a snapshot of what that looks like. So for example, here's the stretch of Burnett Road that they would have driven. The green is the first, or what we refer to as the starting checkpoint. Then as we work our way through, there was a relatively straight checkpoint, then a slight horizontal curve to the right, a slight horizontal curve to the left, as well as an ending checkpoint throughout the drive. And so for each of the 5 scenarios, we replicated these same 5 checkpoints and again measured driver speed and lateral positioning at these different points. Just a little bit more with respect to the experimental design. So we had 20 total drivers, 9 females, 11 males. We required more than a year of driving experience. We ended up with an average significantly higher than that, an average of 11.5 years of driving experience per subject. The range in age was from 20 to 60 years of age, and the average age of our participants in this study was 29.35. In terms of the order in which each of the subjects saw each of the scenarios, we employed a Latin square. Basically what we were doing here was just making sure that each scenario was equally likely to be presented first or fifth or second, etc., to each of the drivers. And again, the idea here was that we wanted to account for any potential order effects. So if the order in which we presented the scenarios had an impact, we wanted to know what we wanted to mitigate for that. So which is why we totally balanced this using a Latin square. And so one of the theories is that as drivers become more familiar in the simulator environment, would they ultimately travel at higher speeds? So that's why we made sure that each scenario was presented in each order across each subject. So in terms of the procedure, they arrived at the simulator. We started with a pre-questionnaire. We fitted them with the eye tracker and calibrated that. We provided some general instructions. Primarily, the instructions were to travel as they normally would, to operate the vehicle as they normally would on the roadway. We also gave them the instruction to feel free to casually talk out loud while they were driving to see if there was anything that we should be made aware of. They practiced with the simulator, so we gave them a test drive in a virtual environment, and we allowed them to continue practicing until they felt comfortable navigating the simulator vehicle. And then we completed the 5 different experimental drives. And lastly, we wrapped up with some paperwork, including both the post-simulator questionnaire, payment voucher, and other materials associated with their experimental. And I should also note that this, was all approved by the Institutional Review Board at the University of Massachusetts, just to make sure that we were being compliant with respect to human subjects research. So some of the results. So with respect to the base scenario, and this is not going to come as any surprise here, I'm showing this more to show how we aggregated this. So here are the 20 total trajectories throughout the drive for each of the subject drivers. The stretches that are shown in the various colors correspond to each of the 5 different checkpoints, and you'll notice there's a general trend that seems to be replicated over and over again for each driver. But one of the things that we know that 90% of the drivers were traveling over at 30 miles per hour, which again not suspecting, and that aligned with the field data that we had for Burnett Road in terms of how fast drivers were traveling. And so we actually have a little bit more in the actual paper where we condense these trajectories and look at them in a little bit more detail rather than at the aggregate level. And we see similar trends, but you'll notice that the paths of the trajectories change just a bit as we introduce a narrower lane. You'll notice that it's not as linear and increasing for the trajectories. But that we still see in the narrow lane scenario that 90% of all the drivers were traveling over 30 miles per hour across the majority of checkpoints. And it's not until we introduce the bicycle lane that we start to see these speeds reduced as part of the drives. And then just lastly, with respect to speed, the raised median, 85% of the participants were above 30, so still a reduction from the base case. And then the curve profile, a significant reduction in terms of the overall speeds that we were seeing. And I'll talk about some of the statistics in just a minute in terms of how we looked at that. And so this is a ton of data here, but let me walk you through this here. So on the left, we have each of our checkpoints. So the start, the straight, the right curve, the left curve, and the end, or the fifth station. And you'll notice that this was how drivers sequenced through each drive, right? So they went from 1 to 5 in terms of the checkpoints, and then as we move across the columns, it's the base scenario as well as the narrower lane, the bicycle lane, the raised median, and the curved profile. And then what you see presented for each cell of the table are the average speeds of the 20 drivers at that particular location, as well as the standard deviation for that. A couple things that I want to highlight here. One, if you take a look at the trend as we move down the rows, you can see within a given scenario what happens to the speeds. And if you look at each of the columns independently, you'll notice that there tends to be a general trend. So if you look at, so scenario 1 all the way through 5, there's a general increasing trend. And same thing for scenario 2, scenario 3, scenario 4, right? And then ultimately scenario 5 is a little bit different profile, but the idea is that the end scenario, the speeds are faster than at the beginning. And then as we move from left to right across this particular graphic, you'll notice that's our comparison. So at that same start point, for each of the 5 experimental scenarios, what was the impact on speed? So for example, at the first checkpoint in the base case, we know that the average speed was 29.5 miles per hour. And in that same checkpoint for the curvilinear roadway section, we know that the average speed of the 20 drivers was 23 miles per hour. And very similarly, in the 5th checkpoint, we know that in the base case, the average speed was 41.6 miles per hour. But then, for example, in the raised median scenario, drivers were traveling 41.2 miles per hour. And so we indicated some of the differences here, and this graphic is really meant to tie that all together. So again, a ton of information, but relatively straightforward. If you give me a second just to go ahead and explain what we're looking at here. So what we have in this scenario is each of the scenes, so the base case, the narrower lane, the bicycle lane, and the raised median, and then the checkpoints. So checkpoint 1 through 5, checkpoint 1 through 5 for the narrower lane, 1 through 5 for the bicycle lane, etc. And we looked at statistically significant differences that existed. And so you'll notice as we compared each scenario to each other scenario, really the significant differences that we saw, and the only real statistically significant differences that we saw were in the curved profile scenarios as they compared to each of the other scenarios. So what I mean by that, the curvilinear roadway environment had significantly slower speeds than the base case. The curvilinear roadway profile had significantly lower speeds in the narrower lane across all 5 checkpoints. Same thing for the bicycle lane scenario, same thing for the raised median scenario. And there was only a couple of other statistically significant differences. One, for example, was the narrower lane versus the bicycle lane. And so when we saw and it was only at that first checkpoint. And similarly, the bicycle lane versus the raised median. So the raised median scenario had a slower speed than the bicycle lane scenario, but again, it was only at one of the 5 checkpoints. So generally speaking, the speeds across the scenarios were and across each of the checkpoints was relatively consistent from a statistical standpoint, with the major difference being the curvilinear roadway profile, where we were able to manipulate and exact changes in speeds. And we did the exact same thing with respect to lateral positioning. And so we looked at the observed mean lateral positions for checkpoints again across all 5 scenarios. And I'll highlight. Oops, jumped the gun here. And I'll highlight just a couple of quick differences here. The narrower lane scenarios resulted in drivers traveling closer to the center line. So when we tightened the narrower lanes, the drivers were shifting their path to be closer to the center line. Which again we may have expected, and we saw some evidence in the final scenarios with both the raised median and the curvilinear profile, where drivers were traveling a little bit closer to the center line as well. And so we did the exact same thing with respect to making all the comparisons. So we compared the base case, for example, to the narrower lane, and the narrower lane had significantly different lateral positioning than the base case. Same exact thing with respect to the base case and the raised median. So in terms of where drivers were positioning, a couple of significant differences, as you can see there, with respect to the base case versus the bicycle lane. And again, all significant differences with respect to the base case and the curved linear profile in terms of where vehicles positioned themselves. And so this is the one that highlights just the specific impacts associated with narrower lane, because the narrower lane was really the most significant factor in terms of manipulating the lateral positioning of the vehicles within the roadway environment. So as we manipulated the roadway environment to make the roadway more narrow, this is where we saw the most significant changes. And again, there's more details that we can share with everybody as part of the full paper in terms of some of the ramifications here. Lastly, just comparing some of the last scenarios, the bicycle lane versus the raised median. There were, as I make my way through these last couple of slides, there was a bit more differences with respect to changes in the lateral positioning from a statistical standpoint than what we had seen with the speeds, and that changed throughout the different checkpoints. So checkpoints 1 through checkpoints 5. So tying it all together here, again, the first one's not really surprising, but we're certainly digging into a little bit more of the data now to identify exactly what we can say about that. And one of the things that we're doing is we're aggregating the trajectories in different ways to see what the influence is on speeds. I mentioned this one over the last handful of slides, but the narrower lanes, participants drove towards the center of the travel lane. In the curve profile, the influence of speed and vehicle lane, the curvilinear profile definitely had an influence. And if you were looking to change a roadway environment, the introduction of a curvilinear roadway has the potential to change driver behavior in a positive way. If again your goal is to manage speeds and slow speeds down as a result of that. There were no differences in driver speed patterns between the base case and the bicycle lane or the raised median scenarios. So that was a little bit surprising, to be honest. We had expected to see that, and so we're still investigating some of what might have led to some of that. One of the things that we didn't do that we might have done or might do in future work was introduce or materialize the presence of a bicyclist. And so one of the things that we found was that in the absence of a bicyclist, or we suspected, was that drivers were treating the bicycle lane like a shoulder, and because they had that nice wide shoulder adjacent to the roadway, they felt comfortable traveling at the high rate of speed that they were already exhibiting in the base case. And so trying to identify some way to account for that, which is, again, something that we think. And then a little bit more interesting was that there were no differences with respect to the raised median scenario. And again, kind of trying to think about what might have led to that. There was, again, a layer of protection that was provided to drivers because they were isolated from the traffic on the opposite side of the road. They felt comfortable. They felt like they had a cushion. And so we could we manipulate the roadway further, but still provide the layer of safety associated with a median, but manage speeds at the same time. And maybe it's the idea of introducing a median with the combination of traffic calming, or we're introducing curvilinear roadway profile, or changing the roadway dimensions while also introducing the median scenario. And that the bicycle and the raised median, again, I mentioned this one, but the wider travel lane has no influence on the vehicle lateral position, which, again, would this be different if a bicyclist had materialized as part of it? So just a couple of closing thoughts, some of the things that we're currently looking to do. One is that we hope to see what the impacts of the new simulator environment may be. And one of the things that we're talking about is whether or not to replicate and run a small cohort of drivers through these same scenarios in the new simulator environment to see if there was something with respect to the fidelity that may have resulted in some of the findings that we're finding here. The other activity that is currently ongoing, although we're a little less certain it's going to yield anything particularly exciting in this case, is the expanded analysis of the visual search. We don't necessarily expect that any of the roadway cross-sectional environments would change the scan pattern of the drivers, but it might be worth taking a quick peek at to see if there is something that would happen there. And we're also working with some of the nearby municipalities as part of some controlled field studies, and in particular taking a roadway environment, studying it as is, and then introducing pop-up bike lanes, introducing narrower lanes. And another experiment that we're excited about is the idea of taking a roadway that currently has no bicycle lane, has a center line down the middle of the roadway, and instead removing the center line and introducing bicycle lanes on either side of the roadway environment. We think that there's going to be something that's interesting with respect to how vehicles align themselves and certainly the speeds that they select. And then, as I alluded to earlier in the study, some of the other things that we're looking at is some of the different curvilinear enhancements and where curvilinear roadway profiles may be advantageous. I mentioned the example of the roundabout entry, and certainly want to study other aspects where that may be most applicable. And so with that, I'd like to thank you and be happy to answer any questions that you might have related to the work that we had here. So Don's asking, thank you, Don, for the nice note, but then asking if we have any perceptions from the drivers. Only anecdotal, so we didn't do any sort of direct analysis on the driver perceptions. The drivers did not really notice that it was the same roadway environment over and over again, which is a little bit intuitive. So it's kind of an interesting question in that just manipulating the roadway cross-section, does that change enough to make the road drivers think that they're experiencing something different? In terms of the speed, we didn't follow up directly with respect to speed related questions, and this is something that we would certainly look to do in future work in terms of whether or not we should have asked get some baseline data with respect to the speeds that these particular drivers would travel as part of the experiment. So Sahar is asking what the reason for the increase in speeds at the end of the roadway environment would likely be. A couple things that are happening there. One, so they've been driving in the simulator for a while. So as they get going, they increase their speed and they're not slowing the speed down. So one is it just as they get going, they stay going and they continue to increase their speeds as they're traveling through the roadway environment. The other is that I know from the graphics it looked like it was a relatively curved road. The reality is it's a relatively tangent section. So as they started out, as they built up to speed, they just continued to stay traveling at that speed. And in fact, we saw that they were increasing the speed throughout the profile as they got more and more comfortable in the driving environment. Great question, though, Sahar. All right. So lastly, I guess I would just say if anybody has any questions at any point, by all means, feel free to email us or contact us. My email is just mknodler@umass.edu. Eleni's is just christofa@umass.edu. We'd be happy to talk to you about the research. And like I said, an open invite to come and tour this. The webinar will be posted, Jacob, in about a couple of days. If you wanted to catch bits and pieces of this again. By all means, feel free to do so. And without anything further, I'd turn it back over to Jacob and the SaferSim team, but thank everybody for their participation today and your attention.
Thank you, Mike. Yep, that was an excellent presentation, and you are correct that we will get this recorded webinar online, within a couple days. It'll be on the SaferSim website and the SaferSim YouTube channel. You can also go to the SaferSim website to, look at all of our ongoing research projects. You can even search, look at this one, find some more, or find the abstract for that. But yeah, as Mike said, feel free to send him or send the Iowa team any questions you might have about SaferSim. We appreciate your attendance, and we hope to see you at future webinars. And with that, we can conclude today's meeting. Thank you for joining.